Hello and welcome. In this video, we're going to talk about volume that's created using known cross-sections. And in this particular video, we're going to focus on cross-sections that are squares and rectangles. Let's go ahead and jump right in. Okay, so let's start by imagining that we have a bounded piece of area, as we can see right here. And we have talked about in previous videos how we can find that area by doing the top minus the bottom, or integrating from 0 to 2 over this particular piece of area. We have also talked about how we could create volume by rotating this around the x-axis or around the y-axis or around another line to create a circle, and we could add together an infinite number of circles to find the volume. But today we're going to talk about what would happen if we actually took a piece of this function, a piece like this, which would really just have a height of negative x squared plus 4 for this particular function. And what if we created a square coming vertically out of this? So the dimensions of that square would be negative x squared plus 4 times negative x squared plus 4. And what if we did that an infinite number of times? And over here to the right, you can see a much better visual than I could try and draw, but we're creating a bunch of squares that are three-dimensionally popping out of the base area. So if we think about making these squares into three-dimensional volume, we're really saying the square is coming vertically out of the base. Each square has a particular thickness, which we could think of as dx, and we would integrate that to find the volume. So integrating the area of all of the squares being added together to find the volume. And this is the basic idea of finding the volume using cross sections. So let's go ahead and look at some concrete examples. All right, so how do we go about finding the volume of cross sections? The first thing that we're going to do when we're reading through our problem is we're going to be looking for, are we perpendicular to the x-axis or the y-axis? If we're perpendicular to the x-axis, that means all things are going to be with respect to x, bounds and functions. If we're perpendicular to the y-axis, that means all things are going to be with respect to y, the bounds, and the function dy. So looking at this example down here, we're looking at this area that's bounded by this quadratic and this line. And the cross sections are rectangles with a height of 1/4 inch that are perpendicular to the x-axis. So there's what I was looking for. Perpendicular to the x-axis means all things x. Since we already have our graph and we know that we're living in a world of all things x, we can find our bounds. So our bounds are going to be x equals -2 to 1. Now let's talk about the area formula. We are looking at an area that is a rectangle. So we know that area of a rectangle is base times height. We know the height here. It actually says the height is 1/4 of an inch. And now we just need to figure out what the base is. Well, the base is this length here. These rectangles are coming outward from this graph. So this length is the base. To find that length of the base, we're just going to do top minus bottom, just like we did when we were finding area between curves. Well, the top is the quadratic and the bottom is the line. So top minus bottom gives us this expression. So our area is going to be 1/4 times negative x squared minus x plus 2. And the idea that we're covering, to find volume, we integrate area. So we're going to integrate from x equals -2 to x equals 1. The area that we just came up with for this rectangle. And we're doing this all with respect to x. Since the integration part is not new, go ahead and pause the video and work through the integration part on your own. Remember, you can take this 1/4 out and deal with it last, and then unpause the video and see how you did. And there we have the work for the integration, which again is not the new part in this section, but go ahead and pause the video, check your steps, make sure you got the correct final answer. So again, the big idea is finding the area of the base, whatever shape they're telling you that the area is, and integrating that area with respect to the correct variable, with respect to the correct bounds to find the volume. Let's look at a couple more examples. Okay, here we go. We're going to set up the integral for the volume of a solid bounded in the first quadrant between 0 and 1. And the cross sections are going to be rectangles that are perpendicular to the x-axis. And then here's some information about those rectangles. The height is 3 times the base. So let's start by doing a quick sketch of y equals e to the x. So here's the area that we're talking about, and I just plugged in x equals 0 and x equals 1 since that's where we are looking, and it's bounded in the first quadrant. So all things with respect to x, let's talk about bounds. It's going from 0 to 1, so we could actually just already set up that part of the integral. The bounds are going to go from 0 to 1, and now we just need to find the area, and we need to integrate that with respect to x. So the area of this particular rectangle is the base times the height. Well, that's the area of every rectangle. This rectangle, we know that the height is 3 times the base. So the base times 3 times the base, or 3 times the base squared. So in order to evaluate this, all I need to do is figure out what is the base. Well, this is the length of the base perpendicular to the x-axis. And what is that? That's just the function e to the x. So the area of every rectangle is 3 times e to the x squared, or 3e to the 2x. So that's going to get set up in our area formula here. And we're not going to integrate this through. You could do this using u substitution, but right now I really just want to focus on setting up the problem for a couple more examples. So let's look at another example. Go ahead and pause the video and create a sketch of the graph that's here, and then highlight the key information. What axis are we perpendicular to? What shape are we using for the area of the base? See what you can identify before we jump in together. All right, so here is our area. We are perpendicular to the x-axis, so that means all things, including our bounds, are going to be with respect to x, and the area that we're looking for is the square. So we can see from the graph that our bounds are going to be from -1 to 2, and if you couldn't tell from your graph, just set the two functions equal to each other to see where they intersect. So all we need now is to find the area of the square. The area of a square is just the length of one side squared. So what we need is to figure out, how do we determine this length? Well, to determine this length, we do top minus bottom. In this case, the top is the quadratic that is upside down, so 2x minus x squared. And we're going to subtract the quadratic that opens upward. And then we're just going to simplify this. This is going to become -2x squared plus 2x plus 4. And this is one side length, and we're squaring it to find the area of the square. And we can put that inside our integral, because to find the volume, we're going to integrate the area of all of the squares. And there we have this problem set up. We're going to look at one more example. Okay, last example, given the graph, I'm going to have you set up A on your own, pause the video and set up A, and then see if you can take a shot at B. It's okay if you get stuck. That one is a little different because it's perpendicular to the y-axis, but go ahead and take a stab at it if you feel ready. Then unpause the video and see how you did. All right, for part A, we're looking perpendicular to the x-axis, so our bounds are going to be the x values, which looks like 0 to 2. So the integral from 0 to 2. We're looking at area of a rectangle whose height is twice the width. So twice the base times the base. So we just got to figure out what the base is, and we have to square it. This is the length of the base, which is being formed by that function, x to the third. So the volume is going to be 2 times x to the third, and the third is going to be squared. I'm going to just clean this up. 0 to 2 of 2x to the 6th dx. Now I'm going to erase all of this because for part B, we're going to talk about what happens if we're perpendicular to the y-axis. So if we're perpendicular to the y-axis, everything should be with respect to y. So our bounds aren't going to be 0 to 2 anymore. Our bounds are going to be from 0 to 8. So volume is the integral from 0 to 8. Now, this function, y equals x to the third, if I solve for x, is going to be x equals y to the 1/3, and that is this length here. The base length that I need, though, is this length here. So using the same logic that we used when we were doing rotation, this whole length is 2, and we want b, so the base is going to be 2 minus y to the power of 1/3. The area that we're talking about on this problem has a height of 6 and a base of 2 minus y to the 1/3. So this is the full area of the rectangle. And we can just plop that in here and integrate with respect to y. We will do more examples with respect to y and examples where we use shapes such as triangles and semicircles in the next video. All right, in this video, we focused on what the volume with a known cross-section is. We specifically did examples with squares and rectangles, and I hope you're starting to see that really volume is just the integral of the area. Go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.